Hello, Team Kestava and the rest of YouTube. I see you found your way to Kestava Engineering. Hopefully that means you're here to stay and learn a little bit more about structural engineering and the type of problems that we tackle on a day-to-day basis. If you're not, well, get your butt in a chair anyway because class has started. You already heard the bell. You're not going to make it to the other, basket weaving class that you were planning on going to. This was going to be a lot more intense, so let's get going. Grab a pencil, mechanical, regular, whatever you want, because today we're talking about snow drift. Snow drift calculations, how to find it, how to determine it, and from there, it's one step closer to designing a full building. So nothing too shabby about that. Before we begin, subscribe if you haven't. Like I said, even if you're still in that basket weaving class, subscribe, because then you've got a little bit of structural engineering knowledge in your noggin. Bring it over to the basket weaving class, and you'll be the talk of the town. All right, it'll only help you. And by the time we get through this video, if you're loving the content, and only if you liked this video, give it a thumbs up. I'd greatly appreciate it. But without further ado, let's get going on today's example. All right, you know where we're headed. So we talked about snow drift. Let's give some criteria here. So what do we got going on here today? Well, we have a flat structure, and what I'm doing is taking a section cut through that structure. So it's a flat roof, and then we have parapets all the way around the structure. So that is this little wall right here. That's your parapet that sticks up a couple of feet above the flat roof line. So it's flat, and let me finish it off here. So that's our ground. What we do need to know are the height of our parapets, which are 3 feet, and then the width of our structure, which we're going to say is 50 feet. So that's what we got going on here today. And what we're trying to find is this. I'm going to go blue for snow, and we want to say, what in snowy, windy conditions, what type of snow loading criteria do we need to design our structure for snow loading? And when we get into drift criteria, that is a combination of wind. So if you think about a blizzard, snow doesn't just fall straight down when it's a blizzard. Very rarely does snow fall just straight down from the sky and accumulate. Winds start to blow, they start to push the snow around, they start to make, depending on where that snow goes, it starts to pile up in locations based on geometries around it and where that snow gets stuck and jammed in. So structures are no different. They are those objects that create those little crevices and corners and nooks where snow can accumulate, and over time you could actually have drifts of snow or big piles of snow that weigh a lot more in critical locations, kind of like right here, where there's much more snow that's loading the structure than you would have in a typical part of the roof in the middle of it somewhere. So that's snow drifts, and we need to figure out, well, how heavy did those snow drifts get, and what do we need to design for in order to accommodate those snow drifts? Now, we've already done a snow load design before, so we got roof snow load design criteria. So in this one, I'm going to go a little quick through that, and it's going to be much more in depth on snow drift design. So at the beginning, if I seem a little fast and I seem to be pulling some numbers from some places and you're panicking a little bit, go back into my previous videos. You'll see roof snow load design. I go real in depth from step 1. Check that one out, then head back in here to talk about drifts. Okay, let's get going. So our ground snow load is going to be 20 PSF. I just pulled that out. It's just going to be someplace in the United States where it's 20 PSF ground snow load. We're going to do an importance factor of 2. So I drew that backwards. So importance snow is 2, which gets us 1.0. Our surface roughness is going to equal B criteria. Again, I'm not going to tell you about these. I will quickly tell you where you get them from, though. So this is in the ASCE 716 manual that we're using today, or provisions. Surface roughness comes from chapter 26.7. Your snow importance factor comes from chapter 1. That's 1.5-2. As we move through the drift criteria and the design, we will be going back and forth to the ASCE 716 manual chapter 7 for snow loads. So we will jump back and forth and I will walk us through the code, so don't panic there. But just at the beginning here, I'm not going to go to these other chapters. We're just going to be jumping back and forth to chapter 7. So when you need some criteria, which I'm showing you here, that falls outside of chapter 7, I'm not jumping back and forth, right? Does that make sense? So I'll just give you the sections for those if you have different criteria. Let's keep going. The structure is going to be fully exposed. That is actually in chapter 7.3-1, so we will peek at that. I'll show you that in a second here. And I think that's everything that we're really going to need. So first two things we need to know, we want to find our flat roof snow load. So PF is what we need to know first before we can then design for drift. So let's jump over to chapter 7. Here we are, chapter 7, snow loads, pretty straightforward. And as you see, if we scroll down here, so this is on page 51, you'll have flat roof snow loads, PF, that's what we have today. We have a flat roof with parapets, don't forget that. So that's where your drift comes in. If it was just a flat roof with nothing, we wouldn't be designing for drifts because snow couldn't accumulate anywhere. Drifts couldn't form. So the parapets are the reason behind why we need to figure out what our snow drifts are. Keep that in mind. And we have our first equation here. So flat roof snow load, PF equals 0.7 CE CT I sub S and PG. Well, C sub E is your exposure factor, C sub T is your temperature factor, I sub S is your importance factor, and then P sub G, that's your ground snow load. So we need to find C sub E and C sub T. We have I sub S, the importance factor is just 1.0, and our ground snow load we know is 20 PSF. So C sub E is first. If you scroll forward here, you will see down at 7.3-1, exposure factor CE, and that can be found in table 7.3-1. So if we scooch on by here, this is that map. So just as a side note, figure 7.2-1, here's your continental United States showing you different snow criteria to find your P sub G, your ground snow load. So we picked, here you go, we picked over here, 20 PSF. That whole region is 20 PSF. Okay, boom, bada bop. Where the fuck does it take us? Did I pass it? Which takes us to page 58, and we have our own little table here. So table 7.3-1, like the previous section said. We have fully exposed condition, so that's just exposure of roof, and that means your building is sitting in the middle of, we'll say sitting in the middle of nowhere. There's no high trees around or other high buildings around that can obstruct wind and snow. And surface roughness we said was B. And again, they even give you a hint here. So see section 26.7 if you need to check that out. And again, fully exposed is explained right down here in the footnotes. So we have B and fully exposed. That gets us C sub E of 0.9 because it's just down and across. That's all that is. That's easy. And you know what? Before we go back, while we're here, look right next to us. Look what we got. Our thermal. So I call it temperature factor. So they call it officially the thermal factor. So C sub T. And if you look through here, it's just another table. And basically it goes through all these different criteria, thermal conditions for structures. So you have structures kept just above freezing. That's not us. You have unheated and open air structures. That's not us. We're going to call this like a small commercial building. So it's definitely not unheated and open air structure. It's not a freezer building. It's not continuously heated greenhouse. So none of the conditions we see here apply to us. So you're like, crap, what do we do? Well, the very first thing right here, it says all structures except as indicated below. So anything else that doesn't match the other options they give you is just a C sub T of 1.0. So you got 0.9 for C sub E and 1.0 for C sub T. Let's get all that info back over on our calculations. So P sub F is going to equal 0.7 times C sub E times C sub T times our importance factor times our ground snow load. All that is going to equal 12.6 PSF. All right, beautiful. Well, we don't. So that's our flat roof snow load. Next, we need to check minimums. So if we go back to the code, C sub E, C sub T, importance factors. So they talk about all the things that you need and where to find them. And then right here, so 7.3.4, minimum snow load for low slope roofs. Okay, well, that is technically us. We are a low slope roof or a flat roof. And if you keep going to the next page, you'll see that where PG is 20 pounds per square foot, PSF, which that's us, or less, so that falls into our category. We are exactly 20. Then your minimum roof snow load, P sub M, needs to be equal to your importance factor times your ground snow load. So let's jump back there, and then before we go back, if you did have a condition where your ground snow load was greater than 20 PSF, then you fall into this other criteria here. So it's all laid out right there for you, but just make sure you realize that there are minimums that you need to design for. So let's go back and check the minimums. So P sub M is just going to be 1.0 for the importance factor times 20 PSF. That is going to equal 20 PSF. Pretty straightforward. So that is PM, and this is PF. So you might be saying, okay, well that means that the minimum, our flat roof snow load is less than our minimum design criteria, so we need to keep moving forward with the minimum design criteria. Well, not so fast. We're going to be using both of these because there's two conditions you need to design for your structure. For snow, you have your drift conditions, and then you have your balanced conditions. For our balanced conditions, we need to design using our minimum roof snow load. For our drift conditions, we get to design using our flat roof snow load that is actually less than your minimum, and you'll see why here, because you don't need to overcompensate, because once we design for drift, we don't have to add that drift load on top of the minimum design load. We get to add that drift load onto the actual flat roof design load that we calculated as 12.6 PSF. Might be a little confusing. I'm just going to keep going with the problem, and you'll see it unfold as we keep moving here. I think by example is always the best for this type of stuff. So now we move on to drift. So first thing we need is our snow density, which is just denoted as density, and that can be found in 7.7-1. So let's go over there right now. So here we are in chapter 7.7. As you can see, it's all about the juicy stuff, the drifts on low roofs, aerodynamic shade. We're not throwing any shade in this class. We are only freaking taking it in, brushing it off, because we're knocking all these problems out. So don't worry about it. But yeah, drifts on low roofs. This is where you need to go. Chapter 7.7 talks all about it and walks you through it. So we have, first right down here, to be completely honest, this right here is where you're going to be spending just about all of your time when you're designing drift. And believe it or not, you might have thought it's going to be a bunch of equations that they're going to show you, but it's actually bulked up in this big beefy text here. So that's unfortunate, but I will be pulling the layers back and using the design example to unravel this whole mess in here. So don't panic yet, because it gets wordy. But first, we need our snow density. And those two equations, as you can see, where snow density is defined here, right there. So let's jump back and plug in that equation to find our snow density. So density is going to equal 0.13 P sub G. P sub G we know is 20 PSF. That's our ground snow load. Don't forget about that. Plus 14, oops, get that parenthesis out of there. Plus 14, that's just part of the equation. Or at a minimum, or at a maximum, 30 PCF. And actually, this ground is 20 PCF. And we'll say min. So it's the minimum of the two choices here. So the minimum of 30 PCF outright, or this equation. So option number 1, option number 2. Well, if we plug in for option number 1, that's going to equal 16.6 PCF. And option number 2 is going to equal, obviously, just 30 PCF. So you're taking the least of those two numbers, which is going to be that one. So that's your density, 16.6 PCF. Good, moving on. Now, I do want to take a pause here really quickly, and let's move back over to the ASCE 7, Chapter 7. I did say that you're going to be spending your time mostly in 7.7, but what I do want to show you is moving forward, we do technically have parapets that we're designing for our drifts. And there is a specific section, as we scroll down here, specifically for, boom, parapets. So chapter 7.8. So you would technically go here first, but then as you read, right at the beginning, first line, the method in section 7.7.1, that's the drift section we were just in, shall be used to calculate the drift loads on all sides of roof projections and at parapet walls. There you go. So it drags us right back there. So we're just going to head back. I want to give everyone the run through of moving through the code diligently. You would go, you say, okay, I have parapets, I have snow loading, I'm looking for drift. There's a specific section. You go to that first, then let the literature guide you back to the appropriate equation. So I jumped a step there, apologies, but that's how you get to it. So here we are back in our lovely 7.7. Next, we need to find L sub U, which is easy. That's just the length of our building. We said it was 50 feet, but let's go write that in. So next we have L sub U equal to 50 feet. And that, I'm just going to go up to the top here. So that is LU. That's your 50 feet. And then, to not confuse anyone here, say you had, so we're looking in plan right now for our structure. And we have parapets, the dashed lines are going to be parapets. We have parapets on all four sides. So if this was 50 feet, but then right here was only 20 feet, your LU would change depending on the snow drift criteria that you're designing for in each direction. So just remember that it's not always the same. If it was a 50-foot square box, then yeah, it would be the same L sub U for the calculations for each parapet of each side. But if you have a different shaped building, just keep track of that. Make sure you're keeping things tight and crisp, okay? All right, going back down. So we have L sub U. And then first we need to find H sub B, and that is the balanced snow load height. And what I mean by that is, how do I want to go about this? What'll be most helpful is I'm going to show you first. Let's go back into the code. And there's a picture that describes everything that we need to find. Here we are. Okay, so page 62. This figure right here, 7.7-2, this is what we're doing right now for the rest of the day. I know it shows a high roof and a low roof, so that's another drift condition, but we have a parapet, and then when we went to the parapet section, it told us we would design just like we would if we had two different height buildings where we're designing the drift for that condition. So this applies to both, and we need to find all these guys. L sub U, we found. You have H sub C, H sub D, P sub D, H sub B, and W. All of those things we're going to be finding. If you have your book there, if you have your code next year, if it's online or something, take a snapshot of it or leave a thumbnail in it because you're going to be flipping back to that a lot. I'm going to keep moving forward here just using these terms, but you might get confused along the way and might start to get lost. So keep this image open. It'll be really beneficial for you. But this is everything that we're going to be finding. Okay, jumping back. So first thing we're finding is this guy right here, H sub B. And like I said, it's the balanced snow load height. Okay, see it back there. And H sub B is just going to be equal to P sub F, so your flat roof snow load, divided by the density of the snow that we calculated earlier, just right up above. For this case, since it's the drift case, we're going to be using P sub F, not P sub M. So we're going to use the flat roof snow load, not the minimum balanced snow load. And that was 12.6. We're going to divide that by 16.6 because that was our density. This is PSF, this is PCF, and what that will get us is 0.76 feet. So that's the height of your balanced snow load. Next, we're going to need our parapet height. We already know our parapet height is 3 feet, so we'll just call it HPPT is equal to 3 feet. Next, we're going to need H sub C, and that is just the height of the balanced snow load to the top of the parapet. So that's an easy equation because that's just 3 feet, the height of your parapet, minus the height of your balanced snow load, which we found, which is H sub B. So that's 0.76 feet. And that is going to equal 2.24 feet. And next, we need to find H sub D. So this is the drift height. And H sub D, this is the guy that requires a little bit of finesse here. Now, there's 2 ways to go about solving H sub D, and I'm going to take you over there now. So if we scroll back up here, so you will see 7.7, section 7.7 will lead us to this figure right here. And what you have is a figure that will solve H sub D for you, your drift height. And if we go to our model here, you see that we already have H sub B, we have H sub C, we have LU, we don't have W yet, we don't have P sub D, and we don't have H sub D, but we're going for this guy, your drift height, okay? So that's where we're at right now, focus on that. Let's go back above here. So it dumps us to this figure. And what you could do is option 1. You could just use the figure outright if your parameters fall within it. And what I mean by that is we have LU, are these numbers here. We have an LU of 50, so here you go. In this example, LU exactly matches one of the lines on the figure. Hey, that's pretty good. We'll go through both options for you. So we have 50. Your ground snow load is the x-axis. That is 20, so that's right here. And then over here, now you have everything you need to find H sub D. So we're going to go up until we hit the line that has LU equaling 50. So right here. And then we're going to go across. I know I kind of sloped it down a little bit, but it aligns actually, if you were to put a ruler on it, with 2. So 2, but it's not just HD equals 2. If you look right here, it's actually HD over the importance factor for snow raised to the 0.5. Or you write that out differently, it can be the square root of the importance factor for snow. So let's go back on that and let me show you what I'm talking about. So option 1 is the chart. And we just walked through the chart, but H sub D over square root of importance factor S. Well, we know the importance factor of snow is just 1.0, and the square root of 1.0 is just 1, and then HD divided by 1 is just 1. So that all actually just crumples out to, and it actually equaled 2 feet at the time from what the chart showed us. And this, because it's square root of 1, equals 1, and then HD divided by 1 just gets you HD equal to 2 feet. Now, if your importance factor was anything but 1, then that changes a little bit, okay? So just keep track of that one. So H sub D is equal to 2 feet. Now, there's one more step for us. If we go back into the code and we go to roof projections and parapets, you'll actually see here, if we read a little further, right here, starting right here. The height of such drifts shall be taken as 3/4 the drift height from figure 7.6-1. Well, that's holy bejesus. That was figures. Holy shit. Stand by. We had a little wardrobe malfunction. Okay. Jeez. I gotta talk to somebody about this. Can we get IT? Can we get IT in here? This is ridiculous. I swear, those guys, we're not paying them enough. They need to be paid more to get them in here and be on hand at all times. We got enough classmates, enough teammates, enough of YouTube watching that we need full access. I don't know what this is. I'll talk to management. You know how it is sometimes, the bureaucracy. But where were we? Sorry. So reading through, the height of such drifts shall be taken to 3/4 the drift height from the figure that we just solved for. So for parapets, it's just right here, i.e. 0.75 HD. So if we go back, well, we solved for HD using the chart to equal 2 feet. So if we multiply that by 0.75, that's going to give us an HD of 1.5 feet. Now, let's do option number 2, which is, we'll call it calc. So we're going to be calcing it out. If you go back, we're going to be going back to the same figure, but if everything didn't perfectly pan out, if we didn't have an LU exactly on that line, or we didn't want to interpolate, they actually provide you down below here with an equation to find the same thing, h sub d over the square root of your importance factor of snow. So this whole equation here, we can plug in LU. Let me zoom in here for us. There we go. Plug in for LU, plug in for P sub J, it's just your ground, and we can solve that way. So let's do that right now. So we have h sub d over the square root of I sub s, again, that's just equal to 1.0, is going to equal to LU, we know is 50 feet, and this was actually your ground snow load, so 20 PSF, and all of that equals 2.2. And as we saw above, for parapets, we need to multiply that by 0.75. So for option number 2, h sub d, and again, we know that the square root of 1.0 is just 1, so that all goes away. So it just ends up being h sub d equals 0.75 times 2.2, which equals 1.66 feet. So you can see the difference between option 1 and 2 is 1.5 versus 1.66. So there's a little discrepancy there. We're going to go with option number 2 moving forward here because it's a little more conservative. The height of the drift is a little bit higher, so hence there's going to be more weight when you're designing your structure. So we're going to roll with that. But now we have everything almost that we need. We need to check one more thing. So let's go back to the code here. Zoom out. If we move back up to this big beefy text, you'll see we have a couple options here. So now we need to find W. W is the width of your drift. So, and again, I know I'm jumping back and forth, but let me go back down to the image because it'll help you out. So W, so let's knock another one out here. Let's erase. So now we have h sub d. Now we're talking about W, the width of your drift. And you find the width of your drift based on some different options here. So we have starting right here. So if this height is equal to or less than h sub d, or h sub c, so we're talking about h sub d right now, the drift height that we just solved for. If h sub d is equal to or less than h sub c, the drift width W shall equal 4hd. Well, let's go back and see. Do we have that case? If we scroll back up, HC we know is 2.24. So if is h sub d less than or equal to h sub c, that would be 1.66 feet, less than or equal to 2.24 feet. That is true. That means that W is going to equal 4h sub d, which equals 6.64 feet is W. So if we go back, you'll see there's more cases. So if this height exceeds, so if h sub d exceeds h sub c, the drift width W shall equal 4h sub d squared divided by h sub c. And the drift heights shall equal h sub c. But however, the drift width W shall not be greater than 8h sub c. So let's check to make sure that we didn't breach our maximum. So they said W max has to equal h sub c. that is just going to equal 8 times 2.24, which is 17.92 feet. Well, we come nowhere close to W max right here of 6.64, so we know we're good. So that is everything. We're code compliant. We follow all the rules. We're within all the requirements. We're good to go. We're moving forward. This is good. Now we have everything we need. Now we just need P sub D. P sub D is the density, or is the weight of that drift stack. So I'm going to go back again to that image because it really drives it home. All right, here's our image. We love doing this. We're going to erase W we have. Bada boom, bada bop. And now the only thing we have left is P sub D. And that is, again, just the actual weight of the drift itself. And that is a pretty easy one. So let's hop right back. Your drift, I'm going to call it our drift density. It's not really our density. It's just our weight, but P sub D, I forget what the nomenclature is. So P sub D is just H sub D, which we worked so hard to find, times your density of your snow. That is going to be 1.66 feet times density of 16.6 PCF. Feet in PCF, that's just going to equal 27.6 PSF. So there you go. There's your unit weight. It's kind of our final answer, but what do all these components mean now? You know, we solved for everything in that figure, but now it's like, okay, well, how do they all come together? So let's go over that quickly right now. So as I was saying way back at the beginning, we have two conditions here. We have our balanced condition, which is the following. This is our roof here. And first, we have just the snow falling straight down. There's no winds blowing it around. It's not a big blizzard. It's just peaceful snow dropping straight down, and drifts are not forming. So it's the balanced snow case. And the snow along your roof here is perfectly balanced. And that height is actually just equal to P min, which is the minimum roof snow load, balanced snow load, which we know equals 20 PSF. So you would design your entire roof for snow criteria of just 20 PSF for the balanced snow loading condition. That's it for condition one. Easy. Next, we have drift. So drift, and I'm just going to draw it blown up a little more so it helps everybody out. Drift, first, we have our snow, our flat roof snow load, but it's not going to be the minimum this time because we also have the drift load along the parapet. So this right here is the parapet. I'm going to erase that just to leave us some space here. So first off, this amount right here is actually P sub F. It's our flat roof snow load, which was 12.6 PSF. So it's less than the balanced, but now we also take into account that drift load, which is a lot heavier at those end conditions around the parapet. Well, we know right here that this is P sub D, and that we just solved for. We scroll back up, which is 27.6 PSF. So 27.6 PSF, he fits it in there. So the total load at the top here is going to be 27.6 plus 12.6. That top is going to be 40.2 PSF. This point right here gets us back the end of our drift and back to our flat roof snow load of 12.6. So that's 12.6 PSF. So here's your flat roof snow. And then above there, that's your drift. And you might say, well, where does that happen? Well, we solved for W, so let's not forget about that. And W is the distance that it happened. W was 6.64 feet. And there it is. So that is your drift condition snow loads. And right above was our balanced snow loads. Now you don't need to combine, so this is why we held on to balanced P min, and flat roof P sub F for so long is that you don't need to double dip here and be overly conservative and just say, well, P min was easy to find, so it's 20 PSF. And then that same condition, you also stack on roof snow drift criteria. You don't combine them here in the same, for the same design. They are separate from one another because that would just be overly conservative. That is it for today. I hope you guys liked it a lot, guys and gals. I hope you liked it a lot. I see everyone while we were doing this problem. I mean, the doors kept opening. People kept coming in. They were way in the back there. I see people eating in the back, drinking coffee. They're wired. They're ready to go, and they absolutely crushed this example, hopefully. But if anyone didn't, don't feel bad. Leave a comment below. Let me know. I'll try to help walk through some areas that I was probably either way too vague on or didn't explain well enough. So reach out. Let me know. If you did get this and you crushed it, leave a like if you liked the video. And this is Rich with Kestava. I'll see everybody in the next one. Later.